Hi, let's go over the solutions for the handout for discussion section this week. The topic of this handout will be on CSPs. In the first question, we'll be asked to formulate a CSP for scheduling professors to classes. For this problem, we're given two entities, the classes and the professors. The first thing we want to do when we formulate a CSP is to figure out which entity is the variable and which entity represents the values. Remember that in the end, we want all of our variables to take on one value, and for this problem statement, we want all of our classes to have one professor assigned. Hence, the variables are going to be the classes, and the variables are going to be the professors. Now we need to figure out the constraints. There's two main types of constraints here. First, not every professor can teach each class, so the professor's qualifications, shown here, poses unary constraints on our class variables. For example, take class 1. We know that Professor B is unable to teach class 1, so we might have a constraint that looks like this to represent that fact. These are unary constraints because they only involve one of our variables. In this example, the constraint only involves class 1 and none of our other classes. The other constraint is that classes can overlap, shown here. We can represent these using binary constraints, which involve two variables. Take class 1 and class 2, for example. Class 1 takes place from 8 to 9, and class 2 takes place from 8:30 to 9:30, so these classes overlap, and the same professor cannot teach both of these classes in the time of overlap. So we have a constraint that the professor we assign to class 1 can't be the same professor that we assign to class 2. Notice that these constraints involve two variables. Hence, we're ready to formulate our problem. We start off by listing out the domains of each of the variables after enforcing our unary constraints. Hence, for class 1, we have professors A and C who are able to teach the course, so let's put that here. For class 2, only Professor A is qualified, so the domain is just A. For class 3, we have Professor B or C. Class 4, same thing, we have Professors B or C. And class 5, we have Professor A or B, shown here. Okay, so the binary constraints are going to be the classes that overlap. And from looking at this section here, the classes that overlap are class 1 and class 2 with this 8:30 to 9 period. So C1 and C2. Class 2 and class 3 also share this 9 to 9:30 overlap. So let's put that here. Class 4 is during the same time as class 3, so likewise class 2 and class 4 also share the 30-minute overlap, shown here. And this whole period is overlapped between class 3 and class 4. So there we have it. Those are our four binary constraints. And we're done. Next, we're asked to draw a constraint graph for the CSP. We start off by drawing a node for each of our variables in the CSP, so that would be C1 to C5. And now we want to draw an edge connecting every pair of vertices that share some sort of constraint. Hence, let's process the binary constraints shown here in order. We first have a constraint between C1 and C2, so we draw an edge between those two nodes. We have a constraint between C2 and C3, so let's draw that. C2 and C4 share a constraint, and C3 and C4 share a constraint. And that's the constraint graph. Notice how C5 is floating out here by itself. That's because it doesn't share a constraint with the other variables. Alright, on to question 2, trapped Pac-Man. Let's go over the problem description first. This diagram shown here will be recurring throughout the whole problem. There's 3 different corridor types, a pit, a ghost, and an exit type. Pac-Man wants to be able to figure out the types of each of the 6 corridors, and the corridors are these boxes shown in this diagram here. From these two statements, we can already infer what the variables and values will be. The variables are going to be the corridors, and we'll label them with variables x1 through x6. And the values will be the pit, the ghost, and exit types. Each corridor generates a breeze. A pit will generate a strong breeze, labeled S as shown here in the diagram. An exit will generate a weak breeze, labeled W as shown here. And a ghost generates no breeze. Let's label this N, and that's actually not shown in this diagram. Pac-Man can stand between two adjacent corridors and feel the max of 2 breezes. For example, let's say Pac-Man stands between corridors 5 and 6. This strong wind that Pac-Man feels is the maximum of the 2 breezes produced by corridors 5 and 6. Pac-Man also knows that 2 neighboring corridors will not both be exits. Alright, let's start by thinking about the constraints for this problem. There are many ways to formulate the constraints, so I'll just describe the one consistent with the solutions. First, when Pac-Man stands between 2 corridors and feels a breeze, he knows that at least one of the corridors must be of the type that produced that breeze. For example, say Pac-Man was standing between corridors 1 and 2 here and feels a strong breeze. Pac-Man knows that either corridor 1 or corridor 2 or both must have been a pit, because a pit produces a strong breeze. Likewise, if Pac-Man was standing between corridors 3 and 4 and feels a weak breeze, he knows that either corridor 3 or corridor 4 or both must have been exits, because exits produce weak breezes. Let's write down the constraints here. So let's take this first constraint. We know that either the first corridor, corridor 1, must have been a pit, or corridor 2 must have been a pit. Notice how this OR function takes into account the fact that both of them can be pits. And we have similar constraints as follows. Alright, let's go back to the case where Pac-Man is standing between corridors 3 and 4. When Pac-Man feels the weak breeze here, he also knows that neither of corridors 3 nor 4 could have been a pit, otherwise he would have felt a strong breeze at that point. The same thing applies for the case of the weak breeze between corridors 2 and 3. We can represent these as unary constraints, where we cannot assign P to x2, x3, or x4, as shown here. Lastly, we need the constraint that there cannot be 2 exits next to each other. That means that for all ij such that xi and xj are adjacent, we have the following condition. We don't want the xi to be an exit and xj to be an exit at the same time. That's it for the constraints. Okay, moving on to forward checking. First, a small note. It's usually easy to apply unary constraints prior to running anything in the CSP, so for this problem, let's assume we enforce unary constraints first. That's easy. If you remember from the previous part, the unary constraints were that corridor 2, corridor 3, and corridor 4 could not contain pits. So we'll just take off P from x2, x3, and x4's domain. And we're done with enforcing unary constraints. We first assign E to the variable x1, and then we run forward checking. Forward checking looks at all arcs pointing to the variable we just assigned. What are these arcs? We only need to consider the variables that share a constraint with x1. For this problem, only the neighboring corridors share constraints, and so the neighbors of x1 are x2 and x6, and we look at the arcs x6 to x1 and x2 to x1. Let's first recall how to test if an arc is consistent. Here's an arc, and here's the tail and the head. We look at each value in the tail's domain. Then for each value in the tail's domain, we look to see if there's a value in the head's domain that satisfies the constraints between the variables. If there isn't, we need to prune that value out of the tail's domain. Let's test for consistency for the arc x6 to x1. Let's try assigning P to x6. Is there an assignment to x1 that satisfies the constraints between x6 and x1? Yes. If we assign E to x1 and P to x6, then the constraints are satisfied. So we move on to assigning g to x6. Well, now we can't assign e to x1 since that breaks the constraint that one of x6 or x1 has to be a pit due to the strong breeze here. So there's no assignment in the head, which is x1, that makes the value g in the tail, which is x6, consistent, and so we can delete g from x6's domain. How about assigning e to x6? Well, assigning e to x1 violates the constraint that adjacent corridors can't both be exits, and so we delete e from x6's domain. We repeat the same process for x2 to x1, and for the same reasons. If we try assigning g to x2, assigning e doesn't work because one of x1 or x2 must be a pit due to this strong breeze here. So we can remove g from x2's domain. If we assign e to x2, then assigning e to x1 doesn't work because, again, adjacent corridors can't both be exits. So for this value in the tail, there's no value in the head that satisfies the constraints, and so we can prune e from x2's domain. So we're done with forward checking. Notice here that x2 doesn't have any values left in its domain, so we can detect this and say that there's no solution down this branch of the search tree, and we need to backtrack. Let's move on to part 3, arc consistency. Again, let's enforce unary constraints right now. So we'll delete p from x2, x3, and x4. Okay, so how arc consistency is going to work is that you put every arc in the CSP into a queue, and then you process the arcs one by one to make sure all the arcs in the CSP are consistent. Upon changing a variable's domain, we have to re-add all arcs pointing to that variable if it's not already in the queue. The ordering of the arcs doesn't matter since eventually we'll have to hit every arc, so let's just use this ordering. We'll start by enforcing consistency for x1 to x2. The domain of x1 is currently p, g, and e, and the domain of x2 is g and e. We try assigning p to x1 and look for a consistent assignment for x2. Either value of x2 works, so we keep p in x1's domain. We try assigning g to x1 and look for a consistent assignment for x2. None of the values in x2 will work, since it violates the constraint that at least one of x1 or x2 must be a pit, so g goes out of x1's domain. We try assigning e to x1 next and look for a consistent assignment for x2. Again, none of the values in x2 will work, since it violates the constraint that at least one of x1 or x2 must be a pit. So we can delete e from x1's domain. Now the arc x1 to x2 is consistent. Since we deleted values from the tail, x1, we have to consider re-adding all arcs that point to x1, which are x2 to x1 and x6 to x1. However, both of these arcs are already on the queue, shown here, and so we don't need to re-add them again. Moving on to x2 to x1. The domain of x2 is currently g and e, and the domain of x1 is just p. We try assigning g to x2 and look for a consistent assignment for x1. Assigning p to x1 works, so we can keep g in x2's domain. We try assigning e to x2 next and look for a consistent assignment for x1. Again, assigning p to x1 works, so we can keep e in x2's domain. The arc is consistent and no values of x2 were changed, so we're done with this arc. Next is x6 to x5. The domain of x6 is p, g, and e, and the domain of x5 is also p, g, and e. We try assigning p to x6. Any of the assignments in x5 will work, so we keep p in x6's domain. We try assigning g to x6. Assigning p to x5 works, so we keep g in x6's domain. We try assigning e to x6. Assigning p to x5 works, so we keep e in x6's domain. The arc is consistent and no values of x6 were changed, so we're done with this arc. Next is x5 to x4. The domain of x5 is p, g, and e, and the domain of x4 is g and e. This is exactly identical to when we enforced arc x1 to x2, so we're going to end up losing g and e from x5's domain. At this point, we have to re-add all arcs pointing to x5, which are x4 to x5 and x6 to x5. x4 to x5 is already on the queue, so we can skip that. But x6 to x5 isn't, so we need to re-add it back, which I'll do down here. We continue doing this until we empty out the queue, so these are the remaining arcs we still have to process. It turns out that no values are pruned in any of the remaining arcs, so this is the solution to one run of arc consistency. In part 4, we're asked to use MRV to see which variable we should assign next. MRV says that we should choose the variable with the minimum number of remaining values. That would be x1 or x5, since they each only have one value left. In part 5, we're asked to think about the solutions to the CSP. We're given in the problem that g is assigned to x6. So we already know the values of x1, x5, and x6. The only three variables left to assign are x2, x3, and x4. There are 8 possible assignments to these variables shown here. Let's think about which of these we can throw out. We have a constraint that neighboring corridors cannot both be exits, so that rules out EEE, EEG, and GEE. We also have 2 more constraints to deal with. First, either x2 or x3 must be an exit, because we feel a weak breeze here. That rules out GGE and GGG as solutions. Next, either x3 or x4 must be an exit because we have this weak breeze here, so that eliminates EGG. There's only 2 possible solutions that we have left, and these are going to be the solutions to the problem. The complete solutions are P, E, G, E, P, G, and P, G, E, G, P, G. In part 6, we're asked to think about an efficient solution to solving a CSP in the form of a ring, which is the structure for the trapped Pac-Man CSP problem. Well, we know how to solve CSPs efficiently if the graph is a tree. Notice how the ring is almost like a tree. If we could just remove one of the nodes, then we would have a tree. So let's make it into a tree using cut set conditioning. We fix one of the variables, let's say x1 for convenience, and try assignments to x1. As long as we make sure to filter out the values from the neighboring variables, that is x2 and xn in this picture, that are not consistent with the assignment we just made for x1, then effectively what happens after assigning x1 is that the node gets removed and we're left with a tree. Now we can run the tree CSP algorithm and efficiently solve the CSP. Here's a diagram representing how the search will look like. At the top, we have no assignments yet. Each of these branches correspond to the assignments on the cut set variable, and the structure remaining at any point in the branch here is a tree. So we can run the tree CSP algorithm to solve this efficiently. In this final part, we're asked to see what the backtracking behavior for solving the CSP is. Using the efficient method we have in the previous part, we know that we don't have to backtrack when we run the tree CSP algorithm. So the only place we backtrack is on assigning the values to the cut set variable, which is x1. Hence, if x1 takes on d different values, the worst backtracking behavior is O of d, because you might have to potentially explore all of these branches here. However, in this question, we're not asked specifically about the efficient method that we had proposed in part 6, but instead, we're running standard backtracking search with arc consistency enforced after a reassignment. So why is it that we're guaranteed that we won't backtrack on the tree? Well, let's first recall the tree CSP algorithm shown here. First, we linearize the tree from any node as root. Then we perform a backward pass. In the backward pass, we check that parent-to-child arcs are consistent. If at least one of the variables has an empty domain, we can immediately backtrack. Otherwise, there's a solution down the path, and then we can do a forward pass of assignments to get our solution without backtracking. Now when we run standard backtracking search with arc consistency helps us ensure that all possible linearizations of the tree have their parent-to-child arcs consistent. So that covers the first two parts of this algorithm. If our consistency results in at least one variable's domain being empty, then it will backtrack immediately on the cut set variable assignment. However, if all the variables still have some values left, we know that there's a solution to the CSP down in this tree. So we get down to what would have been the forward pass of the tree CSP algorithm. So that would be right here. However, using standard backtracking search, we're not guaranteed that we assign variables in a linearized order. But what we are guaranteed is that the very first variable we choose next is the start of some linearized order, since we claimed that we can linearize the tree from any node as root. This means that the branch that we take next will contain a solution. After this assignment, we'll run our consistency again. Well, what's the structure of the CSP after we remove the just assigned variable? Well, what happens when you take a node out of a tree? Let's take this tree here. Let's remove this node, and in doing so, the resulting nodes form either a single smaller subtree or a set of smaller subtrees. In this case, we have a set of two smaller subtrees shown in the boxes here. These subtrees were part of the original tree, so they are guaranteed to have a solution, and after enforcing our consistency again, we get to the exact same situation as we did at first, which is running our consistency on a tree. So through this inductive logic, we eventually reach the leaves and find our assignment without backtracking.